So we're going over a total distance of 6, and we're asked to break it up into 3 subintervals, otherwise known as 3 rectangles. So if we want to break it up into 3 pieces, so we're using 3 rectangles, we need to know the width of each one of the rectangles, like how, what are we breaking it up into? But if we're going a total distance of 6 into 3 pieces, that means the width is going to be 2. Take the total distance divided by the number of rectangles you want, you get the width. Now we need to figure out all the heights. So essentially, if we're breaking it up into widths of 2, we're essentially going from -2 to 0, from 0 to 2, and from 2 to 4. Now, I think I mentioned in the video, you don't have to write down these intervals, but I think they're helpful sometimes. So if you like them, go right ahead. If you don't like them, you don't have to write them down. But that's kind of the intervals we're working over. So our rectangles are going to span from -2 to 0, 0 to 2, and 2 to 4. Questions so far? I'm going to stop more often than I did with my other classes because y'all learned it without me, in a way. Yeah, Jack?
Where do you get the total distance from?
So we're asked to go from -2 all the way up to 4. So the distance between -2 and 4 is 6. And you can also see that by taking your end point, 4, and subtracting your starting point. So 4 minus -2 gives me 6. So that's
Okay.
More questions so far? All right. So we're mostly, well, let me do this too. We're going to essentially need the y values at some of these points, right? Because we need to use them for the heights of the rectangles. So let's go ahead and find out some of those values. So let's just find all the y values at all of the points we could possibly be using. Okay, and we're going to use the function we're given to find them. So -2 cubed is -8, minus 1 is -9. 0 cubed is 0, minus 1 is -1. 2 cubed is 8, minus 1 is 7. 4 cubed is 64, minus 1 is 63. So these are the y values we essentially have to choose from. So now we're set up, we have all the information we need to actually do the sums now. So I'm asked to find a left-hand side and a right-hand side in this case. So if I want to do, what colors did I use on that graph I drew? If I want to use a left-hand side, if I'm breaking it up into the interval -2 to 0, well then the left side of that is -2. I'm going from 0 to 2, the left side of that is 0. If I'm going from 2 to 4, the left side of that is 2. So I want to use the y values at -2, 0, and 2. So if I want to write the areas of those, So see how the intervals I'm working over are -2, 0, 0 to 2, and 2 to 4? If I want the left-hand sum, I want to use the values on the left side. So the left numbers, if you will, are -2, 0, and 2. So I'll use their y values. So we're essentially summing up areas of rectangles. So if you think about the first rectangle, it has a width of 2 and a height of -9. Second rectangle has a width of 2 because they all have width of 2, height of -1, and a width of 2, height of 7. If you're lazy like me, although I wasn't lazy when I wrote it the first time, but if I was doing this by myself, you can put the width on the very outside and then just add up the lengths or the heights inside because you could just factor the width out. I don't remember what that is. 2 times -9 minus 1 plus 7, -6. Don't freak out that it's negative. If you even thought to freak out about it. Questions, concerns on how I got that? Yeah. So the rectangles always go from the x-axis to the function. So they would just go this way and be below the x-axis. And then the ones, I don't think I'm doing the right. And then once we hit here, they start actually going. I'm not doing correct sidedness, but that's essentially what would happen. Is it just switches to be below the x-axis. Yeah, so I pulled this question off the top of my head. And so I'm getting ahead of myself because this isn't until 5.3. But the reason this is okay to be negative, I'll scroll back up in just a second. It's the actual graph I just drew, and I didn't draw the rectangles very well, but just go with it. Most of the area actually ended up below the x-axis. We'll see in 5.3 that any area below the x-axis is actually counted as negative, and any area above the x-axis is counted as positive. So in this case, with this calculation, there was more area below the x-axis than above, so it turned out to be negative. The right-hand side is actually going to turn out to be positive, so it's just because Riemann sums are weird. But in general, if we calculate area for these Riemann sums and these integrals, which we'll talk about today, any area below the x-axis is counted as negative. Any area above the x-axis is counted as positive. Again, that's technically getting ahead of ourselves, but that's technically why it's fine that that's negative. I did scroll back up. There we go. Yeah. Yeah, so we're told to go over -2 to 4. And then I'm told to break it up into 3 subintervals. So if I'm going from -2 to 4, that's a distance of 6. If I break 6 up into 3 pieces, each piece is going to have a width of 2. So if I start at -2 and start like adding 2 to get to my next point, -2 plus 2 gave me my 0 stopping point. 0 plus 2 gave me 2 as my next stopping point. And then 2 plus 2 is 4, which gave me 4, and that was my ending stopping point anyway. Did that make any sense?
Yeah.
So yeah, since the width's 2, we essentially start with the point we're starting with and go in intervals of 2 until we're done. So we're not technically done this question yet because we haven't done the right-hand side yet. Any more questions about the left hand? Yeah.
Based on what you have, I did similar to what you have for x and y. I have like for okay, there's a -2, -1, 0, 1, 2, all the way to 4. Maybe just
So what you're doing is you're breaking it into 6 pieces, which is a different question. So since I specifically say you have to break it up into 3 pieces, that would technically be incorrect. It's a good process, but technically for the question stated, it's not doing what it's asking for. So we would have to break it up into those 3 pieces and no more. So right-hand side, we use the same information, but now, so we're on the same intervals. Like the intervals don't change between the right hand and the left hand sum. But what's the right side of -2 to 0? It's 0. What's the right side of 0 to 2? It's 2. What's the right side of 2 to 4? It's 4. So we're using the y values at 0, 2, and 4. So we'll get a width of 2. And if I can be lazy, -1 plus 7 plus 63. And this is some large positive number, if I remember correctly from the other day. -1 plus 7 plus 63. Yeah, this is 138. Don't panic that they're really different as well. So again, there's the weird thing happening where some of the area is below the x-axis and some of it is above. So with the Riemann sum, it really can be super weird when we change to the other side. And also, 3 rectangles isn't a lot of rectangles in the span of things. So the less rectangles we take, the worse the approximations. So these are actually pretty bad approximations, but they have been calculated correctly. Questions, concerns on how I got that one? Okay. One last thing for this one that I didn't technically ask, but nudge, nudge, wink, wink. I can also ask you essentially a better estimate or the best estimate, you know, some kind of phrase, better, best, whatever. And essentially what you do there is you take the left hand and the right hand and you average them. So if I average these two, add them together, well, so it'll be plus a negative, divide by 2, I'm pretty sure you get 66, if I'm remembering correctly from the other day. Yeah. So that would kind of be the best estimate we can get from 3 rectangles, left hand, right hand side, is we can average them together and get that. Oh, well, savvy. All right, for the next one then, we wanted to find a left-hand sum, but we were asked to do it in essentially 2 different ways. So one is in 3 subintervals and the second is going to be 6. We're going from 0 to 30 in both cases, so the total distance we're spanning over is 30. So if I want to span from 0 to 30 in 3 pieces, each piece is essentially going to have a width of 10. So we're going from 0 to 10, 10 to 20, and 20 to 30. I already have all my x and y values, so I don't have to find them, which I don't have a function. So we want the left-hand side, so we're going to use the values as 0, 10, and 20. So 10, 13, and 7. The width of each interval is 10. So of course you can write 10 times something plus 10 times something else plus 10 times something else, but I'm lazy. So I'm just going to sum up all of the heights. Whatever that is. 300. Brianna, that's kind of like the one we just did, actually, number 1. We weren't given the delta t. Well, I'll talk about that in a second. Let me finish this one real quick, and then I'll babble about that. So that's for the 3 subintervals. Questions, concerns? I don't know how to answer this professionally. I can only think of a sassy answer. Because we're using 3 subintervals. So in this case, we're told to break it into, whoa, excuse you, come back. We're told to break it up into 3 subintervals. So the number of subintervals is going to equal the number of things you're adding together. So if you're only going over 3 subintervals, you should only be summing 3 things. So if we're breaking a total distance of 0 to 30 into 3 pieces, it's going to be essentially sets of 10, if you will, which is why we're going from 0 to 10, 10 to 20, 20 to 30. And then since we're asked for the left-hand sum, I'm going to take the left x value and find its y value. And we're going to use the y values of the left endpoints. So the left endpoints are 0, 10, and 20. So that's, excuse me, that's why I'm only using those 3 values. Sydney, that's the width. So if you think about what we're doing, we're technically adding areas. So, you know, we have some width times a height plus a width times a height until, you know, you have them all. So essentially the way I write them is I write it as the width on the outside and then you sum the heights in the middle. So we know that it's 10 in this case, because again, we're taking a total distance of 30, breaking it into 3 pieces. So that means the width of each interval is going to be 10. So if you take the total distance you're working over divided by the number of rectangles, the number of subintervals, that gives you your width, which is the thing that you multiply the whole thing by. Any more questions on that one before we do 6 subintervals? Okay. Yeah.
Is that simply just like the answer right there is 300?
Yep.
Cool.
So 6 subintervals. What's the width of all of our intervals? We're going from 0 to 30, so a total distance of 30 divided by 6 pieces means the width in each case is going to be 5. So the width's going to be 5. So we're essentially going from 0 to 5, 5 to 10, 10 to 15. Case where I personally wouldn't write these out, but I'll write them out just in case someone likes them. 20, 25, 25. Nope. Remember that space? Ah! There we go. So in this case, we're still taking a left-hand side, so we're going to want the values at 0, 5, 10, 15, 20, and 25. Take the total distance you're working over, divide it by the amount of rectangles you're breaking it into. That gives you your width. So we want to essentially use all of the values on this table except the one at 30. So we'll have a width of 5 because that was our total distance of 30 divided by 6 subintervals gives us 5. And we'll have 10 plus 5 plus 13 plus 2 plus 7 plus 15. I really wish I could just remember what that was. I think it's like 288 or something like that. And 260. So total distance divided by the number of rectangles gives you the width. Works the other way as well. So say instead I actually gave you the width that I wanted you to use here. If you still divide those two things, you'll get the number of rectangles. Also remember for your homework, the number of rectangles is named n and the width is named delta, whatever variable you're working with. Questions, concerns on how I found any of that? Okay, Rihanna, let me talk a little bit more about your question. Example 3 in the notes was somewhat like this one. There we go. The only difference is that that one gave us the width instead of the total amount of rectangles we needed. So say I had asked this question, but I said, let me make that larger so it's like obnoxiously clear where I'm writing. What if I said, let delta x be 6? Okay. So yeah, technically example 3 in the notes gave you the width instead of the number of subintervals, but this process would be similar where you divide the total distance by whatever you're also given to get the thing you don't have, break it up into that many pieces, so on and so forth. So yeah, this is what the quiz is going to be on. This was 5.1. So yeah, any more questions before we move on to 5.2, which is our notes for today? Yeah. So while I leave that up for a couple more seconds, now 5.2 is a very strange section because we don't actually get a lot of new material out of it. And the first half of the things we're going to talk about is literally the only reason we're going to talk about it is so that you can understand a definition that I'm going to write down, and then we're never going to look at that type of stuff ever again, besides knowing that the definition exists. So 5.2 is a little weird. Also, the notation is pretty gross. I'll just be honest. The definition that we're building up to is a very mathematically symbol-heavy definition. Don't panic. It's just a definition. And I'll try to explain it the best I can along the way. So 5, 2. So again, 5-1 was the material in those videos, and it's essentially what we were just going over, Riemann sums. So, sigma notation side note. So we're going to talk about sigma notation. I'm going to tell you how it works, and then we're going to use it to define something, and then we're never going to look at sigma notation ever again. Cool, cool. So, sigma notation. Maybe I shouldn't tell you that right away, because then people will just phase out. Anyway, all right, I already said it. Notation is essentially a way to allow us to write a sum that has a lot of terms in it in a very compact form. So if you think about the things we were just doing, now we weren't going over like tons and tons of terms. We were going over 3 or 6 terms or something like that. But say I asked you to do a Riemann sum of 20 terms, which I would never actually ask you to do, but say I did, then you'd have to write out 20 terms, and that's pretty gross. So essentially what sigma notation does is it writes it very compactly. So it would look something like this, where that symbol in the middle is a sigma. And essentially the thing on the bottom is essentially, so we're going to have something out here. Now this is just essentially, the other thing about sigma notation is the sum has to have some kind of, I don't want to say pattern, but some kind of relationship that all of the terms have. So maybe it's all even numbers, maybe it's all odd numbers, maybe it's all numbers that are squares or something like that. They all have to have like a very similar pattern to how you can write them. So essentially what this is saying, and I'll do one with an actual number in a second, but this is essentially saying this is the pattern that you're following. You're going to start by plugging in 1 wherever you see a k. So just plug in a 1. And then you're going to go up the natural numbers. So 1, 2, 3, 4, 5, 6, 7 until you're done. And you're going to stop when you hit n. So, I don't know what n actually is, so I could just write this generically all the way up till I get to the nth term. Again, I'm going to do one in a number in a second. So it's essentially saying I can take this sum of n terms and just write it like this. So the Greek letter sigma stands for sum, and the index of summation which is k, is going to tell us where the sum begins, and then the top number is going to tell us where it ends. So usually that top is actually going to be a number. Well, anyway. The letters that are used can be whatever letters you need them to be, but I, J, and K are usually the ones that are used. So say I wanted to figure out what this was. So from K to 1 to 4 of, let's do K squared. Let's go away from my notes for a little bit. So essentially this is saying that all the things are going to look like something squared. I'm going to start by plugging in 1, and I'm going to keep going up the natural numbers until I get to plugging in 4. So now I know writing out 1 squared plus 2 squared plus 3 squared plus 4 squared isn't that terrible. But what if it was k equals 1 to 100? Then you wouldn't want to sit there and write out 1 squared plus 2 squared plus 3 squared until you got to 100 squared. But that's kind of how it works. Yeah, I don't know. So writing out something that's like, let me change to I and freak everybody out. This would essentially be saying add all the numbers from 1 to 100 to each other. I don't want to write out 1 plus 2 plus 3 plus 4 plus 5 until I get to 100, and I can just write it like that. So all sigma notation does is take a sum, usually with lots of pieces, and write it really, really compactly. So say I wanted to express the sum 1 plus 3 plus 5 plus 7 plus 9 in sigma notation. Now there's going to be one thing in this piece that you're going to have to kind of trust and believe on me for. Notice that all of those are odd numbers. And remember, we need some sort of like notation to tell us what the terms kind of look like. The actual definition of an odd number. Did you know there was a definition of an odd number? It means that it can be written as some 2k plus 1 for some integer k. So just trust and believe that that's the definition of an odd number, because it is. If you give me any integer, if I plug it in there, it's going to spit me out an odd number. If you give me 0, it's going to give me 1. If you give me -5, it's going to give me -9, which is an odd number. If you give me 7, it's going to give me 15, which is an odd number. So absolutely any integer you give me, if I plug it into 2k plus 1, is going to give me an odd number. All that to say that therefore I can write all of those numbers as some 2k plus 1. So if I wanted to write a sigma notation, all of those are going to take the form of some 2k plus 1 because they're odd numbers. Trust and believe. Once again, we're just building this up for a definition. Well, the first term I have to add is 1. So what k value do I have to plug in to get 1? I would have had to plug in 0. So the first thing we need to plug in is 0. So it doesn't always start at 1. Sorry, all my other examples started at 1. That doesn't have to happen. And then I have to end at 9. Well, what number do I have to plug in for k to get 9? Well, I would need 8 plus 1, so I'd need to plug in 4, so this sum will stop at 4. There's a few other ways you could write this. I did something silly, but I'm not going to tell you what it is because it doesn't matter for the problem. There's a couple different ways I could write this in sigma notation in general, but that works. Okay. So all of that to just say I want to use sigma notation in this definition I'm about to write. This is a scary one, so don't freak out. If you want to freak people out, tell them this definition at parties. Anyway. So suppose we have a continuous function on some interval, as essentially any function we will really consider. Then the definite integral of f from a to b. Now the actual notation for this isn't nasty, but the definition in a second is. So that's going to be written as this kind of really squished s from a to b of f of x dx. So that's what the definite integral looks like. I haven't actually told you what it is yet. But I do want to pause really quick and talk a little bit about the setup here. The a and the b, those are called bounds. I think they have a couple other names, but I'll always call them bounds. Do they have other names? I don't know. And then the f of x is called an integrand. So if you ever hear me say integrand, I mean the function that's in the integral. That dx at the back is actually important, does actually have meaning. In terms of our class, it doesn't, it's just kind of there. The thing it's really trying to do is just tell you the integral with respect to. So we don't do things in this class where we take, like with derivatives, we only took derivatives with one variable. You can also take derivatives with 2 or 3 or 5 or 7 variables and whatever number you want. Same with integrals. You can take integrals with 2 variables, 5 variables, 17 variables. So that's telling you what to take the integral with respect to. In terms of our class, it's just notation. It doesn't really do much for us. So don't freak out about the dx, but it needs to be there. Don't let it go away. So what is this integral? I haven't actually told you what it is. So it's the limit of the left hand or the right hand sum with n subdivisions of that interval as n gets arbitrarily large. In other words, x sub 0 through x sub n are the endpoints of the subdivisions. Let me draw a tiny little picture first. So we have something and we're splitting it up into a bunch of intervals. Okay. So, you know, this is my x sub 0, this is my x sub 1, this is my x sub 2, and so on all the way up to x sub n. So the width here, we're going to think of as some change in x. Like, since I don't have actual values there, I'm just going to write it super generically. It's just the change in those x values. And then if you think about what we're actually using for the height, it's some y value. So some f of x sub 1 or some f of x sub 2. And I say that because I want to write this. So the integral of f of x dx is equal to the limit as n approaches infinity of the sum from I equals 1 to n of x sub I delta x sub I. Did I say it was going to be gross? It is gross. Or, now let me finish writing this grossness out and then I'll explain in babble terms what this is actually saying, because you actually know what this is doing, you just don't realize you know what it's doing. So the only thing that changed between those two is the essentially the bound, if you will, on the sigma. So what the flippin' heck is that trying to say? These in here. And jump over here really quick. Those are the areas of the rectangles. The delta x sub I is a width, and the f of x sub I is a height. So those are areas that I'm summing up. So the sum notation is literally just a Riemann sum. So what this is saying is we're essentially taking the limit of these Riemann sums as n goes to infinity. N is the number of rectangles, so it's essentially saying do a Riemann sum with infinitely many rectangles. Well, that's technically not humanly possible, but we're saying if it's possible, that would find us exactly the area underneath of this function, which we're defining to be the integral. Okay? So what should you pull from this definition? It's that the integral, that notation, means the area underneath of the function. Okay? You can estimate that at this point in time using a Riemann sum. So you can use a regular Riemann sum to estimate those. There will be some of those on your homework in 5.2. It'll give you an integral notation and say use a left-hand sum using whatever. It's the same idea from 5.1. It's just now you've got integral notation in there. Okay. That's the main thing we had to build up at 5.2. So, super scary definition that just essentially says we're taking infinitely many rectangles and adding their areas together. So I've kind of already called them Riemann sums, but this is where I officially say each of these sums is called a Riemann sum. F is called the integrand, and A and B are called the, limits of integration. That's their other name. I usually call them bounds, but they're also called limits of integration. So in 5.1, there was an example. The very last example was essentially we're finding Riemann sums for that function for different widths. So say we actually wanted to write that in integral notation. Say we wanted to take this situation, if t is an hour since the start of a 20-hour period, bacteria population increases at a rate of 3.0.1 t squared f of t equals f of t. And we wanted to write that in integral notation. Well, we have an integral symbol. Let me not write and write anymore. Okay. So we have an integral symbol. And the thing we're integrating over is that rate function. Now my bounds are essentially going to be where's the sum starting and where's the sum ending. Well, we're going over a 20-hour period and we're starting from when it started. So we're going from 0 to 20. And then we always need that notation of d. Now that's d whatever variable you're working over. So in this case, it's dt. If those were x's, it would be dx. If they were y's, they'd be dy. Again, in our case, it doesn't really mean a lot for us, but it does need to be there. How you would write that integral in integral notation. Okay. Questions so far? Okay. The last thing I want to do before we take our quiz, because actually there's a bonus point on the quiz for this, which I realized like a few seconds ago. I'm going to show you how to calculate that in your calculator. Yay. I'm trying to pull up my little calculator doodad. Now, if you have something that's not a TI-83 or 84 or a TI Inspire, I don't know how to do it. We'll have to Google it. But let's see. If we go over. Why is it not letting me pick that screen? Okay, we'll just do this then. So, say you wanted to do the one that we just had. So I know people on Teams can't see this, but we were working with. I know that's like really crappy, but. So say we wanted to calculate that one that I just wrote down. If you have a TI 83 or 84, this is what you'll do. You're gonna hit the math button. You can either scroll down or just hit the number 9 to get that fint option. Notice that my key presses are at the bottom if you missed something that I pressed. Now, if you have a newer calculator, it's going to be super nice because it just kind of lays it out for you. If you have an older calculator, I'll show you how to do it in a second. It's super gross and terrible and everyone hates it. Does anyone have an older calculator in here? Raise your hand. You do? Okay, so 1 second. It's gross, but I'll tell you in a second. So if you have a newer calculator, so it's blinking in the bottom one, so we wanted to 0 as the bottom bound. You can either use the right button, but I like to push the up button to get to the next one because it's up, but the right button also gets you there. Anyway, the top bound was 20. Press the right to get over. You want to put the integrand in there, so you want 3 plus 0.1. Now, for the love of all that is good and holy, I know it's a t. I don't care. Absolutely any variable you're working with, please press this variable button that's right below mode, or else it's not going to give you the right answer. Don't hit alpha and find the x that's in the green. Don't do that. It won't be right. Use the variable button. I don't care that it's an x, not a t. And then we got to square it. Scroll over. Hit the variable button again. And then hit enter. You get 326.67 repeating. 0.6 repeating. Let me leave this up for a few, and then I'll, yeah, okay. If you have an older calculator, throw it out. No, I'm just kidding. So if you have an older one, it's going to come up with fn int. Here's what you're going to put in. The first thing you're going to put in is the integrand. So the thing we're integrating is the 3 plus 0.1. Press that variable button, and you'll have to do caret to, because older calculators. Then you're going to do a comma, which is above the 7. Above the 7 is a comma. So you'll put in a comma, the variable button again, comma, and then you do your bounds. So since we were going from 0 to 20, you'd be 0, comma, 20, end parenthesis. Pray to the calculator gods that you put it in right. Hopefully you get 326.6 repeating. Cool. Yeah.
So when it has a certain number of rectangles that it wants to test, can you take that?
Okay, so at this point, when we're calculating these, this is actually the legit area. So we're not actually considering rectangles anymore. So this, so I'm thinking, so this process, okay, so for the Wiley homework that's up right now, you won't want to use your calculator. There will be Wiley homework in the future that typing it into your calculator will be very helpful for. You'll be able to do it by hand, but it's faster to do it in your calculator. So we will want to know how to do this, but you are right. I believe all of the Wiley homework for this week is technically doing Riemann sums, which you can't put in your calculator. If you have a TI Inspire, you hit I'm going off of memory here. If you have a TI Inspire, hit the menu button. You scroll down to calculus. Oh man, on mine it actually says integral. I think yours it says something like numerical integral or something like that. Yeah. Numerical integral. And the nice thing about that is it also kind of sets it up like the TI-80 whatever, where it just gives you boxes. Now the nice thing about the TI Inspire, since you have that little keyboard at the bottom, if you want to type in T's, you totally can. So the TI Inspire will handle absolutely any variable you want. I usually just default to using X anyway, but if you wanted to type in a T there instead, and as long as it was the T in the integrand and the DT, as long as those match, it'll do it perfectly. So that's that. So if you don't have a calculator that has this capacity, it's not the end of the world. You'll just have to do a little bit more by hand in the future. So if you have a calculator that can do that, try this and see if you can get it. If you don't, just chill out a second. Because again, it's not the end of the world if you don't have one that can do it. But it'll make you happier. And if you have one that's not a TI Inspire or a TI-84, if you wanted to like shoot me an email or something and I can Google it and figure it out. I just don't know how to do it on anything that's not a TI. What do you get when you do this? I didn't count. So you're going to want to be careful on this one because your calculator's old. You're going to want to put that in parentheses. So caret parentheses x squared, or else it will read it wrong. Yeah. You should get 1.46 blah 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 blah. The E, you kind of have a couple options. Savannah, let me jump over here really quick. I usually just do second divide to get the E. There's another way you can get it as well, but I usually just do that one. You can do second natural log and it immediately pops up the exponent as well. But whichever floats your boat, I usually do second division symbol to get the little blue E. So what did I just say it was? Do the thing. 1.46, blah, 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 blah. Anyone in here not get that? Cool. So we're not done 5-2. Well, I should say we're done 5-2 enough that you can do your homework because the 5-2 homework is essentially Riemann sums. So, but we'll do the last two questions in these notes on Tuesday, and then we'll go into chapter 6. We're going to jump around a little bit. We're going to jump into chapter 6 and then jump back to chapter 5 and then jump back to chapter 6. So that's going to be a bit all over the place, but it'll be all right.